Today we're going to see where that determinant can be used, and we're going to look at inverses of matrices. So we write the inverse of a square matrix as A inverse. So only square matrices have inverses, and when you multiply any matrix by its inverse, and it doesn't matter if the inverse is behind or the inverse is in front, you get the identity matrix. So if you want to find the inverse of a matrix, there's a simple little formula, and it uses the determinant. So you have 1 over the determinant in front. The one diagonal gets switched, and the other diagonal stays the same, but each term gets multiplied by a negative. Does that look weird as a formula? So here, A and D get switched, and the B and the C get multiplied by a negative. So if you have a question like this, or like that, first of all, we can find the determinant. This would be 6. This would be 5. So the determinant, if I call this A, would equal 6 minus 5, which is equal to 1. And so the inverse of this matrix, and I'm just going to erase the arrows so I can see what the numbers actually were. If this is A, then A inverse would be 1 over the determinant, which is 1. Switch that diagonal and this diagonal make negative. So we're going to test this. Is it true? Is A times the inverse equal to the identity matrix? So if I take 2, 1, 5, 3, and I multiply it by 3, negative 1, negative 5, 2, what do I get? Well, first row, first column, 6 minus 5, 1. First row, second column, negative 2 plus 2, 0. Second row, first column, 15 minus 15, 0. Second row, second column, negative 5 plus 6, 1. And sure enough, we get the identity matrix. For the second one, this would be 3. This would be 0. So our determinant is, well, I'll call this one B. B inverse would be 1 over 3, and then switch these ones and make these ones negative. And you could leave that 1/3 out in front. In fact, I would recommend leaving the fraction out in front. Or, because it's a scalar, you could multiply that 1/3 into each element and have a whole bunch of fractions. Again, if I want to check if it's correct, then B times B inverse, or B inverse times B, should equal the identity matrix. And one of the reasons I like to keep this 1/3 out in front is because then you can multiply your matrices first. So negative 1, negative 2, negative 3, negative 1, negative 2, negative 3, 0. And the other matrix was negative 3, 2, negative 1. So if I was multiplying these, I can multiply the two matrices first, keep that 1/3 out in front, and I'm going to get 3, 0, 0, 3. And then you can see that when you multiply by the 1/3, you do get your identity matrix. So before we talked about if the determinant of a matrix is 0, it's called a singular matrix. And now, since in our inverse formula we need to divide by the determinant, we know that we can't find the inverse if a determinant is 0. So that's an important aspect of the determinant. If you find out that your determinant is equal to 0, then that matrix does not have an inverse possible. So we can verify our answers with our calculator. If I take one of these ones that we just did, let's say A2153, I go to my calculator, I go second matrix and edit in A 2 by 2. 2, 1, 5, 3. And then on your main screen, you can go second matrix A, and then right above your x squared button is to the -1. 3, -1, -5, 2. Is that what we got? Yes. So you can verify it on your calculator by doing the -1, and it will calculate it for you. So we have a formula for finding the inverse of a 2 by 2 without our calculator. As soon as we go to a 3 by 3, we're going to use our calculator to do it. So what I want you to do is I want you to type in these values into your calculator and then go F inverse and see if you get this value. Yes. 2 calculators. 1, 2. Oh, this is better. This is nice. So now we can solve equations using matrices. And sometimes these equations might have been easier to solve without. Like this one says algebraically, I would probably say, let's subtract these 2 equations because we could use elimination. 4x minus 4x would be 0. -2 minus a -y would be -y. And -2 minus a -11 is +9. So from this, I would know that y is equal to -9. And then I could plug that into either equation. Say I plug it into the second one. 4 plus 9 equals -11. 4x equals -20. And x is -5. So our solution is -5, -9. But we're going to find out that we can also solve this using matrices. And initially, we're going to find out that we're probably like our old system better. Like this wasn't very hard, right? To eliminate a variable and find out that y was equal to -9 and x is equal to -5. How do we do this with matrices? Well, we set up a matrix multiplication. We use the coefficients of your matrices to make a square matrix, a 2 by 2. We use our variables to make a column matrix. And then we go equals, and then our answers get put into a column matrix as well. Does this work? Can you see that this is a 2 by 2 matrix? And this is a 2 by 1 matrix. So the middle numbers match, and matrix multiplication is allowed. And the answer then should be a 2 by 1, and it is. And what happens when I take this row and multiply by that column? Can you see that you would get 4x minus 2y? And does it equal minus 2? That was our original equation, right? 4x minus 2y equals negative 2. And if we look at the second one, this row times this column, 4x minus 1 should equal to minus 11. Okay? So now that you have these matrices set up, what we do is we call the square matrix A. We call our variables the matrix X, and our answers the matrix B. And if we wanted to solve for X, solve for our variables, the way that we get rid of anything, instead of dividing both sides by A, with matrices we can only multiply, but we can multiply by the inverse. And if you multiply by the inverse, well, A inverse times A is just the identity matrix. And the identity matrix times by anything just stays the same. And so we get that X is equal to A inverse B. Number one mistake that students do in this is the following. Okay? I shouldn't have called it a mistake. I should just have done it and then just say, what did I do wrong? Okay? But this is number one mistake. You have this equation and you go, oh, I want to multiply by A inverse. And this is where matrices are a little bit weird. We've already seen that if you multiply a matrix A times B, it's not the same as B times A, right? And so with matrices, if I multiply in the front on the left side, I have to multiply by it in the front on the right side. It makes a difference. Can you see yourself doing that? Yeah, because you're so used to, oh, I'll multiply both sides by the same thing and just put it wherever. But now it's important that this is in the front, this is in the front. If you do one side with it in the back, it won't work. So now we can solve this exact same equation using matrices. First of all, we set up our matrix equation. We've got our coefficients here, x and y, and our answers here. If we let A equal 4, negative 2, 4, negative 1, then A inverse will equal, can you see that the determinant of this one will be positive 4? Negative 4 minus a negative 8. So our determinant will be 1/4. Switch these ones, negative 1, 4. Make the other diagonal negative, so this will become positive 2, and that'll become negative 4. So sometimes I just write A, X, and B over top of those. Then if you have AX equals B, then A inverse AX will equal A inverse B, which means that X is just equal to A inverse B. And now I can write the numbers back in. If I could still see them. Negative 1/4, negative 1, 2, negative 4, 4, and B was negative 2, negative 11. Again, I'll keep that I'll keep that fraction out in front. I'll do my matrix multiplication first without the fraction, just because it's easier to multiply and add if you're not using fractions. Okay? First of all, can you see that this is possible? So 2 by 2 multiplied by a 2 by 1. Our answer here should be a 2 by 1. Row 1 multiplied by column 1. It's going to be 2 plus negative 22, negative 20. Row 2 multiplied by column 1, 8 minus 44, negative 36. And now if I multiply that 1/4 in, I get negative 5, negative 9. And matrix X was our variables. So what does it tell us? It tells us that X was negative 5, Y is negative 9. At this moment, our old techniques look a lot better, right? Matrices will give us another way to solve it, but it's not that much faster with the 2 by 2. In fact, I think it's probably slower. Added to the fact that you just learned matrices today and aren't familiar with them, it's much slower and you don't like it nearly as much. Because the other method you remember and you know how to do and you're more comfortable with. So here's one for you to try with matrices. Even though I can, in my head, use elimination and figure out what X is immediately, sorry, you have to solve it with matrices. All right, ready to check the first one? Set up your matrix equations with the coefficients. Multiply by that inverse in front. Did you get 1, negative 1? Excellent. And if you used elimination, can you see you could have multiplied the second equation by 2? Added the two equations together, added the two equations together and got 5x equals 5, so x is equal to 1. And then plugged it back in and got y is equal to negative 1 really quickly. So I'm not really convincing you yet that matrices are a better way of solving equations. But maybe with the use of calculators and our 3 by 3s, you might like them better. Okay, one more to try. And you're going to have to do some equation work to get it to change into matrices. I've sort of given a hint there to multiply by that multiply by the 4. Okay, if you want to check how you did on this one, after setting things up, finding your inverse, should have got 5 and negative 4. Again, you see that I kept the 1/7, the determinant is 7, out in front until the very end. Then I'm working with whole numbers. Thank you, thank you.
You're welcome.